Okay, welcome back, everyone. We've gone over a lot today and a lot yesterday. We have one more topic on the agenda today, but I hope you'll find it a really exciting one. We're going to talk about some of the cutting edge of text analysis and some new emerging alternatives to topic modeling. Okay, so we described in the last section a lot of strengths of topic models, right? They can do pretty well in picking out some themes, but there's this great challenge of identifying the number of topics and then of interpreting them, right? And making sense of patterns of word co-occurrence through list of words, right? And so those are big challenges. And the methods of interpretation and validation are themselves, even I think most experts agree, not great. So in text networks, we're not going to find a panacea. This isn't going to be an alternative that solves all those problems. But we may find some alternatives that some people may find more intuitive or compelling by thinking about text as network. So we have a very diverse audience. We have probably both experts in network analysis and people who have scarcely ever analyzed a network. So we'll just take a moment to talk about network analysis and how network analysis can be used to do text analysis. Okay, what is a network? A formal definition of a network is a group of nodes. Here, nodes are these circles. Sometimes they're called vertices or a vertex. And then the set of edges or ties between them, these little lines here. And so very often when we're thinking about a network, networks could be all sorts of things, right? In social science, very often a network is a way of representing relationships between individuals. So let's say we're looking at a group of high school students, and each student is a circle, and the edges between them describe whether or not they count each other as friends. And we see very often when we start to think of the world as a network, groupings, just like we see here. Clustering of people. It's one of the few things that seems to be a near universal property of social relationships, is that we see these dense patterns of connections and then these kind of weak ties between them. And without getting too into the specifics of graph analysis, which is of course a huge sprawling field that cuts across many, many different disciplines, and network science really occurs in everywhere from sociology to physics to even increasingly places like political science, economics. And so we're going to have some strange verbiage here and there. But the key thing that I'm going to try to convince you of today is that just like we can use graph theory to find patterns of groupings among people, we can do the same thing with patterns of groupings among texts or people producing texts. So there's an entire field of techniques or methodologies in network analysis known as community detection. And here, essentially, we're writing very fancy algorithms that look for patterns in the ways that people are connected to each other, often by counting the number of paths one has to take to reach everyone else in a network like this one here. And then, very often we can make pretty good clusterings of people into different groups. Here, they're represented by color, because this is a very clear case where we have three kinds of groupings of people. And there's many different flavors of community detection, and that would produce somewhat different results. But the bet here is that if we think about a text as a network, instead of making a bag of words assumption, where we're throwing all the words in a text into a single bin, shaking it around and kind of seeing what comes out, and then making sense of where words are assigned to topics, here we're going to be able to see the words in this kind of more multidimensional connected space, and not only see which words co-occur, but also look for cases of, say, triadic closure. And this is a principle from network analysis where we tend to see that, especially in social groups, where 3 people become connected to each other, we can better identify community structures. And when you think about that, why is that? Well, you may have heard, the old saying, my friend's friend is my friend, right? Or my enemy's enemy is my friend, right? And this type of phenomena where any individual relationship or any relationship between 2 individuals can be profoundly shaped by a 3rd individual, right? A common enemy, a love triangle, whatever you want to call it, right? It turns out that the same intuition can be used to think about words. When we think about 2 words co-occurring, whether or not those 2 words co-occur alongside a 3rd word, this principle of triadic closure is something that has become very central to a lot of theorizing in both sociology and literary theory, where a lot of the early origins of this came out of, and also in linguistics with things like WordNet. And so the idea here is broadly that instead of thinking about people as nodes in the network, we're going to think about words as nodes in a network, or we're going to think about people as nodes in a network, but we're going to connect them not through things like their friendships to each other, but by the way they use the same words. And so we're going to be able to do both something that looks like topic modeling when we connect words to each other, but then also something different, a different kind of grouping that might be more conducive to social science when we're out to group not only relationships between words, but relationships between individual actors in the world. Could be people, could be organizations, could be states, and the way that they talk about things. So in order to make this move from bag of words to these networks of words, we're going to have to understand a core distinction in social network theory, and that's the difference between a 1-mode and a 2-mode network. And for the purposes of illustration, we're going to want to think about a group of newspapers and how they are covering an event, okay? So here in the blue squares, we have newspapers: the Chicago Tribune, the Houston Chronicle, the Los Angeles Times, the Boston Globe, and so on. And then we have these red nodes, and these red nodes are words that each newspaper used when they covered the moon landing, okay? So many of them used the same word, like moon. Some of them used different words, like collect, rock, land. Others use words like mankind, leap, right? This, of course, was a very, very common phrase from the astronaut who landed on that auspicious day, right? And so this is a representation of 2 kinds of relationships, really. It's a representation of newspapers and how they use words, right? That's what we're seeing here. But we can also use this intuition to connect newspapers to each other, or to connect words to each other. And the way that we're going to do that, so here's it explain. So we're going to go from here to here. And the way we're going to do that is we're going to say, okay, the New York Times and the Boston Globe, if you both use the same word, or if you both use a lot of the same type of word, we're going to give you a tie to each other. And if you use a lot of the same type of word, we're going to make that a stronger tie, a weighted tie. That tie is going to have it's going to be thicker, indicating that there's even more of a similarity between the New York Times and the Boston Globe, right? And so we can do 2 types of projections from this, what's known as a 2-mode network, because we're capturing 2 kinds of relationships, right? We can do a word-to-word projection. So here we're looking at how words clustered on that day. Discourse about the astronaut, discourse about the terminology used, and then, of course, how the newspapers covered the event. Okay? So the key intuition here is that, let's say these were not newspapers, but people. And a very classic example is people and their affiliation with groups that comes out of sociology and Ron Breiger's work. So specifically the notion that if I know a person and I know which groups they belong to, let's say Facebook groups, for example, right? And I don't know how people are related to each other in this hypothetical network, but I want to, that's what I'm out to measure, then I can build a network by looking for patterns and who's affiliated with each group. And even though I don't know that the people in the same group are friends, I could make that assumption and create network structure out of looking for patterns of two people being affiliated with the same group. So the same intuition is going in here. We're linking newspapers, in this case, by their use of shared words, and we're linking words by their usage in different newspapers. So we can do two, they're called projections, when we take a complex data structure like this and make it more simple. We can do it with words here, and we can do it with the authors of words, if you will, here. Any questions so far? There's a lot of different, if you're just encountering network analysis, this might be a new concept. Is there anyone in the live stream who has any questions? Okay, great. Okay, so how do we get from there to, from our text to numbers? Because ultimately, to build these graphs, we need to have some kind of numeric representation of words. There's two articles that have done this recently. I should say, though, that the idea of text networks has been around for some time, maybe 20 years, although it hasn't really been developed a great deal until the last 2 years. I published this paper 2 years ago that uses text networks to try to predict the virality of social media posts. And the idea here is that we can take posts. These are social media posts. You can't really read this, so if you're zooming in, I'm going to walk you through it. Up at the top here, we have 3 Facebook posts produced by 3 different nonprofit groups. This was data that was produced using the app strategy that I described yesterday. And these are people talking about autism spectrum disorders in different ways. If you know this field, you'll know that people have very different views about what causes autism spectrum disorders and so on and so forth. And if we wanted to position these organizations in a manner that describes how they're talking about autism spectrum disorders in different ways, we could take their texts, lemmatize them. That's the pre-processing step that I mentioned earlier that's a slightly more sophisticated form of stemming, or reducing words to their conjugate form. Then calculate the term frequency inverse document frequency, meaning that we are rewarding strange words that appear a lot in one document but not a lot in the whole corpus, using our term frequency inverse document frequency. And then we can create ties between all these organizations producing all these posts that describe the sum of the overlapping terms TF-IDF. So what that means is that we're trying to, here we have 3 organizations and these are ties between them. We're trying to say that organizations that use the same words and organizations that use the same unusual words in particular should have stronger ties to each other. And these thicker ties here are going to help us do our community detection, our ability to cluster these, especially these triads of words that co-occur, or in this case, organizations producing words, in order to find themes or groups of authors that are talking in similar ways, or groups of words that together in these clustered networks cohere into a meaning. There's another really nice example that comes from Elise Rule, Jean-Philippe Conté, and Peter Bierman. And this is, they do an analysis of the State of the Union addresses. We're actually going to reproduce some of their analysis in a few minutes here. And what they're doing here is they're taking the State of the Union address, which is a US address that each president makes each year to describe current affairs and what the president thinks should be done about them. And so it's a nice data set and popular in the natural language processing community because it's not too long, and but it contains a real diverse set of discussions. And what they've done in this visual here is plot words that co-occur in these documents. So each node is a word, and each edge is the co-occurrence of that word across a State of the Union address. And remember that there are multiple observations for multiple presidents, so each president might have 4 addresses or 8 addresses, depending on how long they were in office. And so what you can see if you zoom in here is that here we've got the Louvain community detection algorithm applied to this network. That is a particular algorithm that looks again for patterns in the triadic closure and the minimizing the path length or the distance between the edges, looking for essentially groupings of text, right? We see very clear patternings of the words into things you might call topics or themes, such as the Navy, political economy, land, production, domestic policy, foreign policy, crime, statecraft, and so on, right? And so what's nice about this, right, we didn't make any assumptions about K, about the number of topics, right? The Louvain algorithm actually does that for us, which is nice. It's not perfect. Again, just like the goodness of fit measures I talked about earlier, it's at the end looking for patterns of connections, but these patterns of connections are not being driven by arbitrary groupings of words within documents, but we're able to see precisely how not only any two words co-occur in the documents, but how whole clusters of words cohere. So in other words, we immediately see the whole corpus, or most of the corpus, depending on how we visualized it. And this makes interpretation a lot easier. Yeah, we can get a better sense of whether or not there's real signal in our categorization. Okay. Another nice thing about this is, though we could use the structural topic model to get at time, this approach also allows time to be emergent in the classification. So here we have communities that are populated across time, across the State of the Union addresses, and we can look at themes emerge and combine into each other, right? And this is because the dynamic nature of network analysis, right? We can allow for words to co-occur at one period, but then co-occur differently at another period, right? Allows us to look at dynamic shifts in word usage. In this case, looking at shifts in discourse about especially negotiation, arms, the people, the treasury, and how other themes of political debate emerged out of those. So again, it's kind of a nice way of recognizing language as we know it, right? We don't usually think about themes as emerging just through a list of words. We as humans, detect meaning more often by looking at clusters of words and thinking in terms of triadic relationships between words. So, yes, yeah, of course.
I'm no expert on networks at all, but I was wondering the words in the graph on the previous slide, can they end up in different parts of the network, or is one word end up at one location and not any other?
So there's one way of answering that question, which is about the position in the figure. I don't think that's what you're asking, but just in case that's what you're asking, the layout or the way in which the nodes are arranged in this multidimensional space is determined by an algorithm. This one, I believe, is called the Fruchterman-Reingold algorithm, but there's many others like Kamada-Kawai, circle layouts. There's many different ways of positioning the nodes according to their adjacency with other nodes. But I think your question was really about, how does one, can one word only belong to one network, or does it potentially belong to multiple networks? Here's another advantage of text networks, right? Let's look at a word like attack right here, right? It's actually in between our foreign policy community and our crime community, right? Our community detection algorithm will arbitrarily lump it into one of those two things. But with a projection here, we can actually see that it's really in between two topics, right? We could kind of do that with topic modeling. Maybe if we looked at, we did some kind of like Herfindahl style index across topic probabilities and looked at words that had, a high index suggesting they were distributed evenly across a lot of topics. But even if we did that, we wouldn't know exactly which topics they were being linked to and how. And this is just a really simple and I think intuitive way of finding words that are bridging, that may have an important meaning. So the term attack here, and of course it's in between foreign policy and crime, which tells us that this is one of these words that really pivots across the two categories. Yeah. I think there's another question. Yeah.
how do you determine whether there's an edge between two words? I imagine that you would need some kind of cutoff, right?
Yes.
Criterion. So, and maybe you can elaborate a little bit on how it is different to choosing arbitrarily having to choose a number of topics as to arbitrarily having to choose a cutoff for these
Sure.
edges.
I'll get to that particular topic in just a second, but a brief answer is there's no, again, this is no panacea. That is a non-arbitrary decision. But one of the ways that we handle it, which is arguably more informative, is to simulate random networks and then to compare our observed network to that random network and delete edges that wouldn't have occurred according to randomness. And just a shout out to Ryan for recommending that technique to us some time ago. But yeah, I'll get to that in just a second. But again, it is somewhat arbitrary, right? Because at the end, it's not a perfect decision. But the bet is that once we look at it, right, we're seeing what's driving the classification in an arguably more informative way. Yeah. Other questions?
I have a question.
Oh yeah, sure. Sorry. Yeah. May. Yeah.
So like in these political speeches, and I guess other speeches, other document, usually there's like the speaker would cite to other people. So is there a way, is there a way to capture, I guess, the purpose of the citation, right? It could be to criticize, it could be to support, it could be for multiple purposes. And I guess you could do like a sentiment analysis. Is that the way
Exactly,
to do it?
exactly, yeah. And in fact, that's exactly where we're going. We don't have it built into the package that I'm about to show you, but we're just working on exactly that issue. I'll talk about exactly that, applying sentiment analysis to this technique at the very end of this lecture. So it's a great idea. The neat thing is, very often we have social network data. So in the example you're describing, like we know how people are connected, like let's say political parties or something like that. And then we can overlay on top of that political relationship their discursive relationships, right? And then, for example, if we wanted to recast the study of political polarization, we might think of people as people who are in one party but able to speak in the language of another party, right? We can identify those types of people, or those types of, or maybe you're more simply out to identify unusual documents that were influential in bridging multiple communities. That's something I discuss in the aforementioned paper, combining natural language processing and social network analysis to look at in the Proceedings of the National Academy of Sciences.
A quick follow-up, does it also capture the sentiment of ambivalence? That's very often one of the key.
So we're only as good as our sentiment classifier. And as we discussed in the earlier lecture on dictionary-based analyses, sentiment analysis is an imperfect tool. Yeah, but what we're going to do in a few minutes is combine sentiment analysis with part of speech tagging and pick up some of the syntactic relationships between words embedded in sentences to at least connect the word to the object that it's meant to modify to try to do a little better than we would if we just applied sentiment analysis to a whole sentence. Yeah. Yeah, Doug.
Hello?
Yeah.
Okay, great. So my question has to do with whether or not there are standard ways of measuring the extent to which a word is a boundary case. So because these community partitions are probabilistic,
yes.
I mean, if you were to rerun it a bunch of times,
yes.
can you get a measure of which words flip the most? Is there like methods for that?
That would be an interesting way to do it. I mean, that's a little more sophisticated than the way that we've done it so far, which is just to calculate something like a betweenness centrality or some other kind of brokerage measure for those of you who are knowledgeable about social network analysis. But that would be a really interesting way to do it. It would be something similar to doing the goodness of fit measures from specifying K, right? If we reran the community detection 30 times and found the same partition 90% of the time, then maybe we're happy with that partition, yeah. And there's, of course, some community detection algorithms that do that, right? They just take a long time to run. And there's some limitations because we're working with weighted networks here, and so not all community detection algorithms can run on weighted networks. Right now, in the current implementation of this technique, we use Louvain, but we've also had good experiences with the spin glass community detection algorithm, which could be easily implemented in our package that I'm about to describe, but we haven't done it yet. Yeah, but it's a good question. Yeah.
The thought of that method had come from some of the stuff in network neuroscience where they will ask, in this given context, how often is this brain region activated in this task?
Right.
And then when you go task to task, which brain regions turn off and actually.
Exactly, yeah.
So.
Yeah, it's a great idea. I would love for someone to talk to me later about doing that study. Yeah. Yeah. I should say, this is a very new method, so that these type of things we're still working out. But it's a great idea. Okay, other questions? Okay. Okay, so to implement text networks, we've created a package called TextNets. A few of us here at Duke. And it uses a lot of the tools that we've been talking about today to build text networks. It has tools for preparing text for network analysis, doing all that prepping that just like we had in this STM package. It will create the text network, go from words to numbers, creating something called an adjacency matrix, which is necessary to produce a network visualization. It has a series of tools for network visualization, both static network plots like we've been looking at, and also interactive plots where you can mouse over nodes and see which words are driving classification or which authors are being grouped together. I'll show you an example of that in just a second. And finally, it has tools for detecting the words and themes that are driving the classification and groupings. So similar to the layout of the structural topic modeling package, which again is just a great package that covers so much and is really well supported by Brandon Stewart. Okay. So to install the package, you'll need the DevTools package. It's currently living on GitHub. And a word of warning, it has a lot of dependencies, so it takes a while to install. It uses a lot of large packages for things like part of speech tagging and working with large matrices. You'll also, unfortunately, need a very recent version of R. I slacked this to everyone this morning. One of the dependencies in our part of speech tagger requires R 3.5. So you will either need to go to the CRAN website and download a new version of R if you want to try this, or you can use the update R package, which I believe is also hosted on GitHub, which allows you to automatically update to the most current version of R. Okay. And by the way, there's a README on our GitHub, on my GitHub, sorry, produced by several of us here that will work you through a worked example with the State of the Union day that we're about to look at. That is also in the annotated code that is linked on the Summer Institute's website. Okay, so in our package, we attached or included the State of the Union data. And so this should be in quotes here. If you write data and then open and close quotes, SOTU for State of the Union, then it should open up a data frame that has all of the State of the Union addresses for all presidents, I think, up to Obama. One of the downsides of our technique is that part of speech tagging takes a bit of time. So this is a database that only has about 200 authors, but because they're really long texts, they're maybe a half hour, an hour long, our code has to go through each sentence and break it into its parts of speech because we add the option of using noun phrases, noun compounds to tokenize, right? And so in the interest of time, our example is just with the first speech by each president rather than all 4 or all 8 of them. And although it doesn't take that long to run on all of them, it might take 10 or 20 minutes. It's roughly equivalent to the time it might take to do topic modeling, and much faster if you're looking at tweets. And while we're on the subject of tweets, one of the things we didn't talk about when we talked about topic modeling was some of the limitations around sample size. So typically speaking, running topic models on corpuses that are smaller than 800 documents produces very poor quality classifications. Also, running topic models on very short texts, such as tweets or social media posts, also typically produces fairly bad classifications in my experience. TextNets has no limitations in terms of sample size or document size. Obviously, the longer the document, the more accurate the classification becomes, just like topic modeling, but it can be used on corpuses of any size. Okay, so this text, this prep text function is going to read in a a data frame that has a text variable in it. We have to specify the text variable. Here it's called so2text. That's a variable in this data frame. Then remember we can either do a word-to-word projection or an author-to-author projection. Here we're going to create a projection of the presidents to each other. So the presidents are going to be linked in our network based on how many similar words they use. We have another of different options. We're going to tokenize by words. We have options to tokenize tweets, which is kind of nice with hashtags and things like that. We're only going to look at nouns. So here's where we could look at compound nouns or verbs or adjectives or anything we wanted to look at. And some folks here have done some interesting work with verbs. And I think, Jeff, you've done some of that work, right? And we're removing stop words. And we're keeping compound nouns. And we're going to save a file here, just because we might want to rerun it a few different ways. And so here we're creating what we're doing under the hood is creating a tidy text data frame where we only have nouns and noun compounds, and we don't have stop words. And so you can imagine a president, a noun phrase, a president, a noun, and so on and so forth. And we're going to use that, pass that to the next function called createTextNet, which is going to take that tidy text object and transform it into a network object called in R iGraph. And there's also an iGraph module in Python if you're familiar with network analysis in Python. And once we have a iGraph object here called so2textNetwork, we gave it a new name now in this stage, then we can visualize the text. The visTextNet function is going to read in that text network. It has a parameter that we've specified here called label degree cut. So if you have a really noisy network with a lot of different people and you only want to visualize the people who have a lot of connections, for example, you can specify the degree. Degree is a measure of the number of connections each person or each word has. And then you can only visualize the labels of. Here we've labeled everyone, and so we've set that to 0. To Karsten's earlier question, right? Because everybody would use a really common word like United States, everybody would have a tie to each other. And so if we just plotted the whole network, we would see a giant hairball, right? It wouldn't be very informative at all. Now remember though that we're using TF-IDF, so we are penalizing really common phrases like United States, and we are rewarding really strange terms, right? That may be characteristic of a particular president. But at the same time, even after, and topic modeling does that, as we discussed earlier, we're still going to wind up with a hairball. So here, underneath the hood, the visTextNet package is using something called a disparity filter, which is what I mentioned earlier. We're simulating random networks, and then we're comparing the random network to our observed network and keeping those nodes that do not appear purely according to chance. And that's localized for each node. There are other alternatives like K-core connectivity, but we found in recent testing this is working really nicely. So here you can see the patterns of co-word usage by the presidents. And what's really nice here is you can see almost perfectly picked up time. So down here we have Obama, Bush, Ford, Carter, Lyndon Johnson, Kennedy, and back up here, Grant, Thomas Jefferson, George Washington, Andrew Jackson, John Quincy Adams, and of course, movement through the 19th and 20th century here. Particularly in very dense networks, this type of static visualization can be constraining. And so the TextNets package also has an alternative called visTextNet D3. And this creates an interactive visualization in your RStudio pane, in the viewer pane, that looks like this. And you can drag over individual nodes in order to reveal the name of the author of the document. Or if you're doing a word-to-word projection, you can mouse over to look at which words are driving the classification. And if you'd like to save these HTMLs, you can come back to our slides here. Using the HTML widgets function, you can use the save widget function and specify the name of an HTML file you'd like to save. And of course, these could be embedded in presentations or RPrez scripts and so on and so forth. Now, one of the complications, so earlier Carson had the good intuition that just as topic modeling has a problem with identifying K, the number of topics, we still need a number to specify at which point we're going to prune the ties that didn't occur according to randomness. We have a tuning parameter called alpha here, and alpha by default is set to 0.25, and that's how we get this nice projection. But if we turn up the criterion and make it harder for someone to have an edge, we wind up trimming nodes, right? We don't see all the presidents here, and we wind up with a less informative network. So there is a kind of balancing act of finding that sweet spot for alpha, and we haven't yet done benchmarking to do that, and that would be a great next step for anyone who wanted to take it. To analyze these text networks, we can run our Louvain community detection on the network, and then look at the groupings of presidents. So here we see modularity class, which is the cluster. You can think of it as the clustering. And of course, as Doug mentioned, we could use a probabilistic grouping or probabilistic community detection assignment. So here you're seeing old and new presidents grouped. And we can do the same thing with the words. So this is just analogous to topic modeling, right? Earlier we looked at which words occur in which topics and which documents occur in which documents. We're doing the same thing here. And so here we're seeing how different types of themes occur in different modularity classes. Modularity classes are, again, groups or clusters of patterns in our network. We can also calculate the centrality of given words or given authors in our network. In the aforementioned paper, my 2016 paper, I show that the centrality of an actor in this cultural network, if you will, is strongly associated with the virality of their social media posts, accounting for all the other confounding factors we talked about yesterday. So, okay, finally in the last few minutes here, so there's some exciting next steps that we're taking. So now that we've got the parts of speech tagged, right? We've been, in these examples, just looking at nouns and noun compounds, and we talked about how that's maybe an improvement over tokenizing by words or unigrams. But we can go a lot further, because part of speech tagging not only tells us the parts of speech, but we can also use sentence parsing to identify the dependencies of words upon each other. So we can know which word in a sentence modifies which other word. So our example, I hate the president versus I'd hate to be the president, right? We can, through sentence parsing, pull out the part of the sentence that we care about, right? In this case, president, and then pull out the adverb modifier, and then run a sentiment analysis on that adverb modifier. And to May's earlier question, that allows us to then either create a valued edge, so we can say two people agree about most things or they disagree about most things, depending on whether their shared sentiment around an object is either positive or negative. Or we can look globally, we can treat each person as a vector of opinions across all different nouns or objects or named entities they might talk about, and then calculate some type of dissimilarity score between them, rewarding or making stronger ties between people who talk about the same topics in the same way, and penalizing people who talk about the same topics in different ways, and deleting edges between them. Yeah? So here we have a toy example where the authors here are all talking about a series of silly things, and we're drawing edges between us here as a proof of concept. And now, just last week, we've been applying this to Twitter discourse that we collected in the other study, the bot-based study that we described yesterday. And here, this is a plot that by Fridolin Merhut that shows really interesting patterning according to our valued networks. Or these are here dissimilarity between words based upon this combination of sentence parsing, part of speech tagging, sentiment analysis, and network analysis. And so if anyone is interested, we're very much looking for collaborators, people who might want to apply it to their own corpus or suggest improvements. And some have already been suggested here today, which we'd love to follow up with you on. We're almost out of time, so I think I better pause for questions here or on the live stream. Anything? Carson.
Cool package.
Thank you.
Did you consider also using named entity recognition for stuff within texts?
It's a great idea. We find that a lot of those get picked up as noun compounds, but in an earlier version of the package, we used phrase machine, which uses more sophisticated type of named entity recognition. The problem we were having is that it has these weird Java dependencies that make it difficult for people to use. And we found that in most cases, people were doing okay with noun compounds. But it could be easily tweaked to incorporate named entities. And that would be great, because they could then start to infer social relationships from text data at a more sophisticated level. Maybe that's where you were going with that suggestion.
Yeah, just as a follow-up, so maybe in the future it would be possible to, for example, specify the backend for text parsing so that you could not only have UDPipe for example, SPACY, and Python dependencies are working much better than Java dependencies, in my opinion.
Yes,
And this might be a solution.
Absolutely. We've been impressed by UDPipe. I agree, SPACY, when we installed a Python backend for SPACY, we saw better results as well than the Java results. But check out UDPipe. The nice thing is it allows support for multiple languages too. It's another advantage of our package, we think, is you can specify the language, any language that's supported by UDPipe, and I think there's, about a dozen, Frito, or some? Six, okay, well. 16, oh, even better, okay. 6D, whoa, okay, wow, all right. So not bad, yeah? And that's another advantage, right, of thinking through this technique, is maybe it's more portable to other languages, yeah. Human languages, that is, yeah. Python, who knows? Yeah, someone write the Python module, yeah. Okay, any other questions? We should probably wrap up, we're out of time, but I have a few announcements. The first is tonight at 4 p.m., we don't have a speaker here at Duke, but there are two great speakers, one of whom I mentioned earlier, which is Ned Smith at Kellogg, who's doing really interesting work at the intersection of social psychology, social network analysis. And the other is Arthur Sperling, who's a political scientist who's been at the frontier of text analysis. He's at NYU. He's talking at the NYU stream tonight. Unfortunately, they're both talking at the same time at 4 p.m. And of course, here again, tomorrow we'll have David Lazar, and then on Friday, Sendel Melanathan, and then next week, Dean Freeland, Christian Lum, and Monica Lee.